Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over again trends in the ionization energies of different elements, and we're going to kind of explain exceptions to those trends a little bit. So let's get into this. So here in this problem we're told that the first ionization energies of phosphorus and sulfur are 1060 and 1005 kilojoules per mole, respectively. This does not follow the general trend across the periodic table. Explain these values in terms of electron configurations. Okay, so the first thing I want to talk about is what exactly is the trend in first ionization energies as you go across the period from left to right. And the trend is that you should know is that as you go from left to right, the ionization energies, the first ionization energies, meaning that the energy that's required to remove the first electron increases as you go across. And the reason for that is as you go across the periodic table, right, what's increasing? The number of protons in the nucleus. So if you are going across the periodic table in a period, each successive element increases its number of protons by 1. So the effective nuclear charge of the nucleus is growing, meaning it's got more positive charge. More positive charge means more attractive force on the electrons, and therefore it's going to take more energy to remove the first electron in the valence shell. Okay, so as you're going across, the nucleus, the positive charge of the nucleus is growing larger. The attractive force on the electrons is getting larger. Therefore, it's going to be harder to remove the electron to overcome that stronger attractive force. So, going across, you would expect the effective nuclear charge to increase, and therefore ionization energy increases as well. Okay, so that's the general trend, and that's the explanation for the general trend. Okay, so why is it that phosphorus and sulfur don't follow that general trend? So if you look at the periodic table, you'll see that phosphorus comes before sulfur. So you would expect sulfur to have a higher ionization energy than phosphorus, meaning that it should take more energy to remove the electron, because supposedly the electrons are feeling a greater pull by the nucleus compared to that of phosphorus. But we see here that phosphorus actually has a greater ionization energy than sulfur. Sulfur has a less ionization energy, slightly less, right? Not a whole lot less, but it's still less. It's not following the trend. Why is that? Let's look at the electron configurations. So the electron configuration for phosphorus is going to be 1s2, 2s2. Where's phosphorus? Yes. 2p6, 3s2, and then 3p3. And then for sulfur, it's 1s2, 2s2, 2p6, 3s2, and 3p4. So notice here that for phosphorus, the subshell the p subshell has 3 electrons. Well, what's the most electrons that a p subshell can hold? It's 6. Why? Because the p subshell has 3 p orbitals. Each orbital can hold 2 electrons, so therefore the maximum is 6. And here we have a half-filled orbital, or I'm sorry, half-filled sublevel at the p. Here we have 4 electrons for the same p sublevel, and so we have 4 electrons filling in those 3 orbitals. Here we have a half full sublevel. Here we don't have a half full. So what you should know about half full sublevels and completely full sublevels is that those sublevels are going to be generally more stable than what you would normally expect. So here, if we can get a clearer picture, if I do the orbital diagram, right? So if I do an orbital diagram, we have 1s here, then we have the 2s at a higher level, then we have the 2p orbitals, the 2p sublevel, then we have the 3s, and then we have the 3p. Now, both of these have everything the same up to 3s2, so everything is full. So we're going to add electrons, spin up, spin down, spin up, spin down, spin up, spin up, spin up, spin down, spin down, spin down, spin up, and spin down. Now for phosphorus, it only has 3 electrons in the sublevel. Now, according to Hund's rule, if you remember, if you have 3 orbitals that are at the same level, same energy level, the rule is that you fill in 1 orbital at a time with 1 electron, all the same spin, before you pair them up. So here you'll see that for phosphorus, I have 3 electrons in the sublevel. So each of the 3 electrons will have its own orbital. You're not going to pair them up. This structure here has good stability. So this is going to be more stable than if we start pairing up electrons. One of the reasons for that is because when you pair up the electrons into the same orbital, you're going to deal with repelling forces, right, which are unfavorable, right? That's going to raise the potential energy of the atom. And so more higher potential energy means less stable, and therefore this is going to require more energy to remove the electron. So what I want you to understand is in this situation, we are removing an electron from a situation where it's relatively stable, given that we have 3 electrons in the sublevel, making it half full. Again, the key here to understand this is that a half full sublevel has more stability than you would normally think, right? So because this is a more stable situation, if you were to remove an electron from that, that would not be a stable situation. So that's going to take more energy to remove an electron in this situation than this situation here. Why? Because in this situation, for the sulfur, we have another electron. So if I have another electron, it's going to go into the p sublevel, and now I'm going to pair up the electrons. Now, this is a less stable situation because now I have electrons that are together in the same orbital, and they're going to be repelling each other, and that creates a less stable situation, right? So what happens if I remove this electron? If I remove the electron from this situation, what happens? I am now, right, if I remove the electron here, if I remove that fourth electron, what do I end up with? I end up with a half full sublevel, which is an especially stable situation. So this is favorable. Removing the electron is going to make a more favorable situation. And that's why it's easier to remove the electron, right, from the sulfur, right? Because you're actually creating a more stable situation, and that's favorable. And so that's going to lower the potential energy of the atom. And so because then you're creating a more stable situation, removing that electron is going to be easier because it would like to have this situation more than it would like to have that situation. Okay, oops, that should be spin up and spin down. Going back to the phosphorus, so remember, phosphorus already has a half full shell. So removing an electron from this situation is going to be less favorable and therefore not energetically favorable. So it's going to require a little bit more energy to remove that electron to create this. Now, this not as stable, right? It doesn't like to have this situation. So that explains why removing an electron from sulfur, your first electron from sulfur, is actually requires less energy because you're creating a more stable situation. Whereas in here, you already have a nice stable situation with a half full sublevel, and removing that electron will create a less favorable situation. So that's going to cost more energy. So that's the upshot to understanding that that discrepancy in the general trend of ionization energies as you go across a period. So I hope that was helpful. If that was helpful, if that helped clarify things for you and you enjoyed this video, then by all means, like the video, share the video, hit that like button. Also, do me a favor, subscribe to my channel. Do that now. Do it now. Also, hit that notification bell. When you do that, click all. And so that way you can be notified by all the videos I put out. Finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you need help with a problem or you have a question, put that down below. If you have a topic you would like me to cover, let me know. I'll like to do that for you. Thanks for joining me and have a great day.